In this video, I'd like to look at some examples of logarithmic equations that are going to use method 2, where both sides of the equation are contained within logarithms, and then because logarithmic functions are one-to-one, we can simply drop the logarithms. In this first example, the process is very straightforward. We just have a single logarithm on the left-hand side and a single logarithm on the right-hand side. I should point out the base is the same, so for both of these we have base 8. That's important. The bases need to match. And then again, because logarithms are one-to-one functions, the only way for the output of the logarithmic function here to be the same on either side is if the arguments equal each other. And that gives us a simpler equation to solve. So I can just gather the x's together, subtract 2x from both sides. We get 2x minus 6 equals 7. I can add 6 to both sides. So 2x equals 13. And so the answer, or at least a possible answer, is x equals 13 over 2. But before we conclude that that is an answer, we need to check. We should plug it back in and make sure that both sides are positive. So 13 over 2 is like 6.5. And if you look at what happens on this side, 6.5 times 4 is going to be 26. And then minus 6, we get 20. So that's the argument inside here. So we end up with log base 8 of 20. On the other side, 6.5 times 2 is 13. And so we end up with 13 plus 7, which is also 20. So on both sides of the equation, we end up with log base 8 of 20. And so it checks out, right? This is an actual solution. For the other equation, we need to do a little bit of work first. On the left-hand side over here, we have two separate logarithmic expressions. So we can use the product rule to gather together the two logarithms on the right-hand side, and we end up with log base 10 of 6x minus 9. We know it's base 10 because there's no explicit base given. On the other side, using the product rule, we end up with x plus 1 times 7 inside the logarithm. And so we have log of 6x minus 9 on the one side and log of 7x plus 7 on the other. And now, since we have single logarithms on each side, we can basically let the logarithms undo each other. Again, this is because logarithms are one-to-one functions. So the only way for what comes out of the logarithms on both sides to equal each other is if what's going into the logarithm is the same. Right, so the only way for this to be the same, what comes out of the logarithms, is if what goes into the logarithms is the same. And now we have a linear equation we can solve. We can subtract 6x from both sides. We end up with negative 9 equals x plus 7. And then I can subtract 7 from both sides. And we end up with negative 16 equals x. So again, that's a possible solution. We need to plug that back into the original equation to determine whether it's actually a solution. And what you notice pretty quickly is that if I plug in negative 16 for x, I'm going to end up with log of negative 15 here as one of my expressions, and I can't take a log of a negative number, so that's not going to work. And what that means, sadly, I guess, what that means is that there is no solution. This is the only possible solution. Negative 16 is the only possible solution, but it fails to be a solution to the original equation. And so we can conclude for this second example that there is no solution. So our first equation had the solution of 13 over 2, and we checked that out and it worked in the original equation. The second equation had negative 16 as a possible solution, but it didn't actually work in the original equation. It's an example of an extraneous solution. I hope you enjoyed the video. Thanks for watching.